All right, so the first question I have for the group here is I'd like to know, with just a raise of hands here, how many folks here are technicians that are new to a UNOLS vessel in the last 4 years, or even to a vessel in the last 4 years? Because this is an introduction supposedly for new technicians. So for those of you that are familiar with Samos, a lot of this is going to look really, really, really familiar. But I will be going over some stuff that we can discuss, review, update, etc. I wanted to introduce myself. I'm the director of the Marine Data Center at Florida State University, and I've been running the Samos program now for almost 20 years. I'm amazed we're still doing this, but it's because it's, I believe, very beneficial to the techs on the ships that we keep doing this for you. It's also great for our user community that wants the data. My other person I wanted to introduce who's online is Kristen Briggs, my co-author on this. She is my lead data analyst. So she does her work from a office in Pennsylvania, but she's been working on quality control for the UNOL ships, particularly the NOAA fleet, specifically for the last decade or more. So what is Samos? It's a data stewardship initiative. Our goal is to improve the quality of meteorological and near-surface ocean data collected on research vessels. I will add the caveat that we're looking at doing this on merchant ships as well. There's some efforts we're doing with Science Rocks to look at getting this on, doing our work on commercial ships as well that have automated systems on board. Our user community, and I'll discuss this more in some of the later slides, we are very much focused on some science goals related primarily to air-sea interaction, understanding the exchanges of heat and moisture and energy from the ocean and the atmosphere. We also have a big user community that is interested in benchmarking satellite data and improving the quality of satellite observations as well as numerical models. So the data that we're collecting through the Samos program from your vessels is being used by a wide and diverse user community. It's also being used in process studies, a number of other activities. So the Samos project, as I mentioned, is almost 20 years old now. Experiment. FSU is the marine, or we were the data center for the weather observations from, and in WOS, the ship is out doing. So in 2003, there was a workshop program. In the intervening years, we have expanded to having funding from the National Science Foundation through the R2R project. And now the Schmidt Ocean Institute provides us funding for the Falcor previously, and now the Falcor 2. We have a strong international partnership with Australia through the IMOS project and New Zealand. National vessels that we have in the Samos program right now. So just as a kind of an overview of the fleet, some of this I just mentioned, the different funding agencies that are supporting different ships in the fleet. What you're looking at here are just cruise maps from 2022 for the ships and where they went. And so the data, a lot of it is collected around North America because we're US centric in terms of our fleet primarily, but we have ships down in the Southern Ocean because we have the US Antarctic Program vessels. We have the Investigator from Australia. We have the Tangaroa from New Zealand. This year. So we are trying to, have data that's global. And we also, which gets us up into the Arctic. I'm just curious, is somebody monitoring the chat? Because I see chats, just want to make sure. Okay. So this is how the data actually flows. So the data actually comes off the vessel to us in a daily email message. Now I'm going to go into more detail on the next slide about how what the data sampling rates are. Possible to 0 UTC. Once it hits our site, it's automatically merged with metadata from a ship metadata database that we have, put in a common data format. We're using NetCDF for our data. It undergoes our automated quality processing, and that happens within seconds of us receiving the email. That data file is made what we call a preliminary file. It's made available to the user community within a couple minutes of your data getting to our. A 10-day delay, we produce what we call an intermediate product. This is where we take all the files we receive for a specific ship for a specific day and smash them together into a single daily file. Because as you know, data transmission isn't always nice. Sometimes we lose data, sometimes we get the same data twice, so we get different file pieces in the preliminary data. So we actually have that merge process to get rid of the duplicates and put everything back together into a nice, neat daily file, which we call this intermediate file. For about, go back here. For about half the fleet that we have in Samos, there's another step of visual quality inspection. That's what Kristen does mostly for our group. And those go through this visual quality control and additional flags are added. So that creates a product. And you'll see those A's on the files there. All of those files are what go to the National Archives. So all this data ends up at NCEI in the National Archives. One thing I was going to mention, and Jasmine noted this with Coriolis, there should be another arrow coming off the ship heading over to this ship database. I haven't added it yet. That are actually sending us metadata along with the data from the ship. And we are now in the process of being able to automate the processing of the metadata, as well as looking into doing metadata quality control to look for differences in metadata on data. On the vessel, this is within whatever acquisition software is on board the ship. That creates what we call this Samos data set. The ship's sensors are configured however they're configured on board the ship, but as a good example, a lot of the sensors are recording at 1 hertz. So the ideally is 1 minute in. Our preference, and in that you'd basically be taking the 61 hertz samples, averaging them together, either using vector average or scalar average, depending on the parameter, which one would you. An instantaneous value, like for rain rate or something, makes more sense. And in that case, basically the acquisition system will go in and pick one of those 1 hertz samples every minute and send that to us as a spot or instantaneous value. We can take either. Our software will handle it. It's really up to how the systems are configured on the individual ships. These data get put together in a Samos exchange format. It's a CSV file. Some of you have probably seen it. It basically has a bunch of key value pairs. So you have a key, which we call a designator. That designator tells us this is the atmospheric pressure from a certain sensor on the ship. And then the value follows it. And that's how our software can go in and automatically take these files, parse them up, and get the data into the right place in the NetCDF file. I already noted the transmission, but the other thing I'd note is that for NOAA SCS 4.9, SCS 5, and for Coriolis, Samos processing is fully integrated in. Other ships that don't have those acquisition systems have had to build their own custom software to create that Samos data message. And there are a number of examples out there, Woods Hole, Scripps, all the different acquisition systems have something built that they have built to do it. I took ship. It goes through our preliminary processing. Either Kristen or I look at that data every day. It comes off the ship for every ship in our system. If we see a problem, we're emailing the technician on board the ship. This is the number one thing that we're doing to help you guys do your job. You know, when you're out on a biology cruise, you don't have time to look at whether or not the anemometer is working. They probably don't care for what they're doing on the ship on that science. And we try to make sure that, you know, we have another set of eyes, you know, backing you up from the shore. I mentioned the archival of the data. This is just a lot of information. I'm just putting the slides so you have it, you know, when the slides are distributed. Just want to make sure it's clear that the data is going someplace. It's available from our website, our FTP server, our Threads server. We're working on putting it up in an ERDAP services, you know, through another project. And then all the data goes to the National Archives in Washington for permanent 100-year archival and access. The NCEI data has a DOI, it has a landing page, it's citable, you know, if somebody wants to go and cite the data for publication. The graphic on the side is really it's just one of our internal tools we use. Those A's tell us whether or not it's been shipped to the archive. Which data have been archived and received confirmation from the National Archive. So the real question is, you know, why do we care? What's the importance of these data? You know, what are they being used for? And I talked a little bit, and some of you have probably seen this slide, but this is an example of how we use the data or how our user community uses the data. This is an example of a comparison using Samos data to the HICOM model, which is an ocean model. The ocean modelers used the shipboard data to determine that the river plume, this freshwater plume coming out of the Mississippi River, was being basically showing that the water was way too salty in the Gulf of Mexico in the model. It wasn't handling the river plume correctly. And so they actually went in and retuned the model to handle these freshwater inputs better. So that's one example. Another example here is where another user is taking the data, matching it up to satellite observations and using it to improve the retrieval algorithms they're using to calculate humidity and air temperature at the surface of the ocean from space-based radiance measurements. So they aren't obviously the satellite. The data is also going into a lot of global syntheses. One example is the International Comprehensive Ocean Atmosphere Data Set. This is the largest database of ocean marine weather data in the world. And so the data is, we actually take the Samos data, we subset it further and actually submit it into this data set. Also going into something known as and put it out in their data product. As I mentioned, we have a strong focus on air-sea interaction, what we know as fluxes, the exchange of information between the ocean and the atmosphere. We produced a flux product back in 2016 using the Samos data that was published. It's available at NCAR. It's also traceable via DOI and a publication. And right now there's another NOAA project that's funding us to actually redo that product, update it, and bring it up to the modern day, known as Marine Flux. So the data, again, are getting used in a number of communities. Another tool that's being developed this is a tool where, again, there's this big user community that wants to co-locate in situ data with satellite data. And what we're working on is developing a cloud-based user tool Basically, it's a series of open source software that somebody can actually install or have up on a cloud environment that actually allows them to draw a string box on a map, pick what satellite they want, pick Samos data, pick a couple other data sets, and they'll get back a co-located sea temperature data set for satellite and in situ data. So this has been a project that I've been working on with NASA for the last about 6 years. Propulsion Laboratory is looking to make this an operational tool in the next few years. So at this point, I'm going to pause. There's an opportunity for questions. That was kind of the overview. Any questions so far? Things that don't make sense? Everybody's awake still? I know I'm fading. I was awake at 3, so. Anything in chat that I need? I see a lot of chats, but it's mostly technical issues. Yes, absolutely. I will get some water while you.
Every like 20 to 30 seconds, there's a
I see. I've been seeing the internet as stable.
is it?
Things.
Okay, let's remove literally everything online except for the Zoom and see if that makes a difference.
Okay, and we're back. Hopefully the folks online, I apologize if things were breaking up for you, but hopefully this will be better now. So one thing I did want to clarify, I had forgotten in the introduction there. What's different between Samos and the Voluntary Observing Ship program? Some of you are probably, familiar with the fact that your ship is not only sending us Samos data, but you're also sending data to your National Weather Service. So in the US, there'll be, you'd be shipping it off to NOAA, or in Australia to the Australian Bureau of Meteorology. The two programs are asking for data basically from the same sensors. Now we got feedback. I've got an echo. Hopefully it's gone. So what they basically want is observations from the same system, so the same instruments on board the ship, but the two different programs have two different requirements in terms of their user community. Weather forecasting and safety of life at sea. So they need the data off the ship in as close to real time as possible, but they don't need it as often. Generally speaking, they want the data maybe once an hour, because that's what feeds into numerical weather forecasting and the numerical weather models. They also they follow the WMO's kind of requirements for sampling. They want something like a 2-minute mean. They want it observed within so many minutes of the top of the hour. This is all part of the requirements of the World Meteorological Organization. So they're supporting operational forecasting. Samos, our rule is we're slightly delayed mode. We want the data at higher temporal frequency. We want an observation every minute. But our user community, as you can see, numerical modelers, satellite CalVal, these people don't need the data right now. They can look at data historically. So there's a slight difference in the user communities. Does that make sense? Other questions? I always have to clarify that because it does come up. So moving on, how does what we do benefit you as the operators? And we already talked about at-sea notification. We're monitoring that data every day and checking for quality. And if there's a problem, we let the operators know. Ideally, this problem can be fixed before, a whole cruise worth of bad data is collected. But, there's operational realities. Sometimes we email the ship and tell them a sensor went south. I actually did that today. One of the ship's temperature and humidity sensors went out to lunch. But they had just left port. I expect they're not going to be able to do it. Metadata tracking, that's another thing we've been doing for a long time. As we are moving toward automating getting the metadata at the same rate we're getting the data, we're going to be able to do more in terms of making sure the metadata is up to date with the data we're collecting, but also being able to check the quality of the metadata. How does it change over the course of time? Things I'm not going to spend a ton of time on, but we do training. So we have educational opportunities for technicians. I run a marine meteorological training course. Some of you might have seen that last year at RV Tech. One of my graduate students actually ran our training course along with Kristen. And then the other thing we do a lot of is decision support for vessels. We'll come out to your vessel, look at where your instruments are, or we'll do it virtually. We'll give you recommendations on putting the sensors in good exposures. We'll even give you recommendations on the types of sensors we recommend for purchase on board ship. So these are the kind of things that we do to help improve the data quality. Just a few things on lessons learned. So this is an example. The shoreside monitoring really does work. This is an example from one of the vessels, and if you can see in the data here, I warned you these graphs are small. The ship was actually saying that the true wind direction was about 110 degrees or 100 degrees from 110 degrees. But when we compared it to a nearby buoy, as the ship passed the buoy, the winds at that buoy are coming from 300 degrees. And you can also see on the, you can also see on the satellite image, the winds are coming around this big circulation here. So again, off of San Francisco, we can infer that the data are coming from that northwesterly direction. Here's an example where we can use satellite data to determine that the ship's anemometer is having a problem. And we can contact the ship and they can work on repairing it when time permits. Quality control isn't perfect. This is another thing we have to deal with. We actually have something we do, it's a land check. We basically check to make sure that the latitude and longitude say that ship's sitting over the water. Only problem is it's only as good as your land mask. We're currently using the eTopo 1 minute arc minute land mask. It will not resolve small rivers and ship channels, like in this case where the ship went through the channel that splits Cape Cod off there. So our data quality control flagged that data as the ship not being over water. In this case, our visual analyst will go in and remove those flags. That's why visual inspection is a very useful tool. The visual quality control is very important. When we can do it, generally speaking, will add 5 to 10% more flags to the data because there's so many things that only visual analysis can actually find. It's very hard to automate for all the possible things that can happen on a ship. Airflow over a ship, as we all know, is very, very chaotic, and it has a huge impact on atmospheric sensors. And so one of the things we've been advocating for now for well over a decade is fluid dynamic modeling of the airflow over ships. This is actually an airflow model run by Gloston early on in the RCRV design. And this was implemented for the Zakuliak. We recommend it for every new ship when it's being designed. Just did it for the new Antarctic vessel, made that recommendation. It allows us to make changes to the instrument masts and make decisions on sensor location with having this high quality modeling is really, really important and really makes a big difference in getting the sensors in a good location. Never enough metadata. Metadata. The more of it we can collect, the better. This is actually an example of, and I'm going to say right off, no criticism to any of the operators when you see me, saying a specific ship here. This is not a critique of the ships. This was just an example where they had 2 sea temperature sensors on the ship. They had one at the intake. They had one up in the lab. So we're getting the sea temperature from the 2 different sensors. They swapped the sensors, but we didn't get an update to the metadata. So we didn't know that the sensors were swapped. And what you're seeing is a calculated difference between the sea temperature in 2 different time periods. And you can see it's basically inverted the graph. And if you're a user of the data, you have a big problem because you don't know, which one's the one that's at the intake and which one's the one that's inboard on the ship. So one of the things we really push for is making sure your metadata is up to date. The work that the folks are doing at SCS, Coriolis, all these different data acquisition systems, to make it easy for the technicians to get the metadata into the system so that it propagates down with the data is a huge, huge step forward. The more of that we can do at acquisition, the better the data is going to be down the road. Some of the things that we learned through the years, as we've been doing the Samos project, is we weren't collecting enough metadata on some of these sensors. One of the examples is the sea temperature sensors. We now collect a lot more metadata about the location of the sensor. We originally collected just the information on where is the sensor, XYZ for where that sensor is. Well, that's fine if the sensor's next to the intake, but if it's in the lab, having the XYZ of that sensor, a TSG up on the water wall, is not useful if you're using the sea temperature and somebody thinks it's out at the intake. And as we know, the water temperature will change as the water comes from the intake, goes through all those pipes up to the lab, the temperature changes. So now we're actually collecting the location of the sensor, the location of the intake, and the length of the pipe run. How far is that water traveling through the ship? This is all useful information for the users. Another thing we've started doing is, and this started with the SCS5, we're actually capturing the associations between data. For calculated parameters, especially the true winds, it's very important for us to know exactly which navigation system is providing the speed over ground, heading, course over the ground that's being used to correct or adjust that wind observation. Because a lot of ships carry 5 or 6 navigation systems. If you change it and we don't know it's changed and we don't know the association, then the true winds are likely going to have problems. We're very focused on operator best practices. We have been since the beginning. It's part of the training we do. These are just some of the kind of top 5, kind of lessons learned through the years. When it comes to meteorological sensors, the rule of thumb is as high as possible and as far forward as you can get it on the ship, you're more than likely going to get better data. Yeah, it's just a rough rule of thumb. Obviously, you've got to avoid your RF and other types of electronic noise. There are certain sensors that are very sensitive to it, radiometers being one of them. And this is becoming a bigger and bigger issue as more and more ships have more and more satellite, comm systems and other things on board. Obviously, avoiding sources of heat. This has been fixed, but this was a long time ago. An example of a temperature and humidity sensor that was deployed above an air conditioner. Doesn't work real well. So these are the kind of things we have to, we go out when we do vessel visits. These are the kind of things we try to find and fix. Documentation, and then of course the true wind calculation. I'm not going into that today, but if you have questions, feel free to come and find me while I'm here. We can go through the details. It's not easy. It's very easy to get it wrong. The equations are nonlinear. Yes, really quick, but yeah, getting those done correctly is really important. Another gap for questions. Anything? It's a quiet bunch.
The present license that we're using are obsolete. Still
Talking like the
athletes. Yeah. And I've heard some others that they're using, but I didn't notice. Somebody's going to maybe help me out here, but I thought those were only they seem pretty simple. And I know the equities have all these corrections, especially the long wave one, as you were saying, which is also very sensitive to noise. I guess my question is, do you have any comments, or is there a sensor we should be moving to? Are these other ones working?
Sure. So the question had to do with the radiation, the light sensors, shortwave, long wave that are on ships. Epley has been off and on in the throes of going out of business for a while, I think. But I think they're still functioning. But there is a question of being able to calibrate those old Epley sensors. And so there is a push in the community to move to different sensors. I'm not going to recommend anything right off the top of my head right now, but what I am going to mention is they're one of the best practice groups. There was a big effort in the international community to draft a best practice for shipboard radiation measurements. There's actually a paper that I and about 40 other people are co-authors on that is going to be going to Frontiers probably within a month. And it actually goes through and lists all the manufacturers of the top rated radiometers and which ones they recommend. And it what's your requirement for radiation measurements? Are you doing this to meet the baseline surface radiation network, you know, NIST standard kind of accuracy, or do you have lower requirements? And it actually takes you down a branch and you can figure out which sensors are the best ones to purchase. The one thing I would note is that there has been a lot of work recently on using aspirated, fan ventilated radiometers, and they're showing a lot of promise in terms of keeping the sensor more stable and also helping with a lot of the contaminants on they keep it cleaner. They help deal with frost. They have to help deal with some of those issues you get, you know, so obviously cleaning radiation sensors is really important. So, other questions?
But just to add to that, our issue's never been with the F-lease, it's been with the RMR RAD acquisition boxes that the F-lease plug into. It takes them like months to get calibrated. Sometimes you get them back with incorrect coefficients.
I'm sorry.
Yeah. So the question had to do. Yeah, the question had to do with RMR Co. It's a company, a small company out in the Pacific Northwest that built an interface board for those anemometer or for those radiometers. That company, the person who founded it has retired. It's also having some questions about whether or not the company is going to continue. So I think there are some issues with those being out there in the community. Some of that I think is also in this best practices paper, but I do think there are some good sensors to swap over to. And some of them are there are some that are capable of not just doing direct solar, but diffuse solar, which is also very important in the radiation community. There's a new low cost sensor out there that's showing also a lot of promise for that as well. So, anything else? Okay, oh, go ahead, Robbie.
Just wondering if something I think I've heard before from you is the sky cameras. Any thoughts on doing that more? Cameras are cheaper, data is easier, but that's you. I'm not sure you're the one that wants them. I think the other group.
The question was whether about sky cameras, and sky cameras are really designed for measuring cloud cover. Give you an idea of the clouds. And actually, where the community is going, the shipboard community is going, is to LiDAR. And actually, the RCRVs are going to be all equipped with ceilometers, which are LiDAR cloud measurement systems. And there's actually, I believe the Sekuliak and a couple other operators have been asking about putting ceilometers on ships. The air-sea flux community is very interested in these sensors. They have become robust enough for shipboard deployment. They've been used in research ship deployment for a while. And now they think they're ready to go prime time as an operational system on ships. And they will give you cloud height and cloud cover.
Once a day.
Yeah, they actually are continuous measurements. So it's a pulse. It gets, you get a I'd be a question, I think, more for Jasmine and working with the Coriolis stuff. The backscatter data is pretty big. That might not be able to be transmitted in near real time, but the measurements of cloud height, boundary layer height, that kind of stuff, those are just single values. So you can get that stuff back, just like any other serial string. Yeah. Other comments? Okay, so the rest of this time, I really was just going to go through some examples of problems that we've seen recently that you may or may not have, seen on your ships. So this is just kind of partially this is kind of fun stuff, but I think it's worth taking a minute to just show you what happens in the real world. So this is actually data from one of the vessels operating in the tropics. And so what you're looking at here is the relative wind speed from two different sensors. So there's a redundant sensor. You'll notice these ones are upwards of 20 plus meters per second. The other sensor has somewhere around 5 or 6 meters per second. The redundant rain sensors, you see this big chunk of rain data that's happening. The other sensor's not recording rain at all. And then on the right-hand column, again, you see the problems with the wind sensors again. Down on the bottom is a shortwave and long wave radiation, and you see this big jump in long wave radiation happening at night. That got me scratching my head when I was looking at it. I was like, what in the world is going on? And so I, emailed the techs, and the techs were like, well, bird is the word. So these are great photos. I have a whole host of them from the Atlantis and from the Thompson. So what's happening here is the birds are coming in to roost at night. And so on these ships, they have WXT weather stations, which have a sonic anemometer. The birds block the sound pulse going from across that. They have an acoustic rain sensor. Feet tapping on the acoustic rain sensor. Okay, there's a problem. And then of course there's nice warm bird butts sitting on your long wave radiometer. So here's the problem. So Pause MV thrashing. Yes, I'm sure Jules is very familiar with this one. So what we see are these big jumps in the platform speed. So again, you're seeing the platform speed up there on the top, on the right-hand side, upwards of 50 meters per second, I believe. And that of course affects the true wind calculations. And again, this is something that Kristen's worked more with than I have, but how do you pronounce that? Aplenix, yeah. They're aware of the problem. They pushed a firmware fix, but evidently it didn't completely fix it. So we have still been seeing this even after that firmware fix, but I'd have to check with Kristen to see when most recently she's run into it. But just be aware, it's out there. It's
so Jules wants super accurate heading. That matters first. But for the wind speed, would we be better off using a gyro that's more reliable but not quite so accurate?
I think for the winds, actually gyro is fine. I mean, here that's how it was always done before. We got into GPS type navigation systems. The gyro was the primary. Sometimes it was even a magnetic compass that was being used for the true wind calculations. And because we're doing 1 minute averages,
that they put in made a huge difference. We've seen a very dramatic
reduction in those thrashing events, and there have been a few cases where we thought it might be like that old thrashing one, and it's a different kind of problem.
Okay.
So I think it's great.
Okay, great. Yeah, Jules, for those that didn't hear, said that from their experience, the firmware fix has done a good job of fixing the thrashing problem, but there might still be something else going on rare occasions. So another example, this one here is on the top, you're seeing the atmospheric pressure, and you're seeing that, again, there's these big 1 to 2 millibar swings in the atmospheric pressure data. There's no real corresponding changes to temperature or wind speed. This is one of the things that is very important when you're looking at weather data. Usually if there's a change in one variable, there's a corresponding change in another variable if it's a real physical thing going on, a frontal passage, a storm passing, something like that. So, the question was, what's going on in this case? Well, this is a case where the pressure tube coming out of that barometer was cracked. And so because there were cracks and gaps in the pressure tubing, of course, that's now allowing wind and air to blow. It's like not having a gill pressure port on the end of your tube. You're now getting dynamic pressure, fluctuations. Just Fixing the tubing solves the problem. So again, that's just a maintenance thing. You have to remember to periodically check the tubing, make sure it hasn't gotten brittle and started to break. Another example, also with pressure, this one here, what you're seeing on the bottom is the range of the pressure in a diurnal cycle. And the pressure range on this day is, it starts at about 1,010, goes up to 1,018 or so. It's about a 10 millibar range. Comparing to nearby buoys the ship passed, the actual range was only about 3 millibars. So this again was, a question of why is the ship seeing this big range in their atmospheric pressure? Turns out it was moisture in the tube. And so again, when you get things inside that tube, it'll affect, the water's not as compressible as air. So you get some problems. Clean out the tubing, problem solved. This one is another example. This example here, you'll notice there's two different anemometers on this ship. And you'll see that there's a difference in the wind direction, about 60 degrees difference between the top, between these two sensors. Oh, I'm jumping ahead in the way this mouse works. And again, looking at the other data that we had, it was notable that this was happening when the temperature was dropping below freezing. And so what it turned out was that when the temperature was dropping below freezing, you were getting ice buildup in the junction box. And you're actually getting moisture intrusion into the junction box. And so then you'd have icing and then it would melt as the day, went on. So then when it melted, that it would look better, the winds would look better, and then it'd freeze again. There were just all these weird things happening. Once they cleaned out the water out of the junction box, dried it all out, sealed it back up, problem was solved. So again, just very strange things you can see in the data sometimes. Here's another example of long wave radiation. Long wave radiation should be in the, about 50 watts per meter squared to about 400, 500 watts per meter squared. This is all negative, minus 700, not reasonable. In this case, and this was something that Katie Watkins Brandt helped us diagnose. When you look at the actual raw data messages, there's a case and a dome temperature with these radiometers, these long wave radiometers, and they generally should be pretty close to one another. You can see here they're 28 and 67 degrees. That was an indicator that there's something wrong with the dome, and it's either that the dome is leaking or compromised, or with a compromised seal, or something's wrong with the thermistor. But if you're familiar with the data messages and the individual data instruments on the ship, knowing what to look for in terms of what you should be seeing in these data messages helps you diagnose some of these problems. This last one, this is a case that I worked with the folks on the Ravel with. Was another interesting one that we thought we knew what was going on, but then when we looked a little closer, it was a little bit surprising what we were seeing. So this is a case where you can see the ship is actually on a cruise. This I think actually was a Clivar cruise. So they're stopping, every 40 or 50 miles to do CTD work. So the ship's going, it stops. It's going, it stops, so it's doing over the side work. And what you'll see is their bow thruster room, they have a Seabird 45 and a Seabird 38. And every time they stopped, there was all these spikes in the data. Lots and lots of spikes in the data. And then as soon as they started moving, it looked good. It matched up with their hydrolab sensor. So the first thought was, oh, okay, well, the bow thruster must be operating while they're on station. To do station keeping, we're getting bubbles or disturbance somehow from the bow thruster. Well, the technician confirmed that the bow thruster was not on and not actually running when we were seeing this situation. And so, but he did go and confirm that there was air in the line. There was definitely bubbles getting into the system, even though the bow thruster wasn't on. It turns out that what it was is it had to do with not just the direction of the waves hitting the bow of the ship. It was very critical which direction the swell was coming from. And in this case, when the ship was traveling slowly and traveling against the swell, they had the spikes. When it was traveling with the swell, they didn't have the spikes. So just a very, very subtle change in the orientation of the ship with respect to other parameters can make a big difference in the quality of the data. So that's all I have. Open for any other questions about what we do, how we can help you all. Anything online? Okay, I guess we're done.
Thank you, Sean.
You're welcome.